Okay, so let's start on today. As I told you earlier, that we will first go over the asymptotic notation, big O notations, omega, and all this, because these are very important to analyze algorithms. These are the tools. Okay, probably you know about it, but let's go over it again. Okay. So let me write one very small and simple program, which is called say matrix addition. Okay. So this is mat add. It takes two array A and B, double dimensional, and n is the, suppose it is the matrix by n by n. Then suppose this is the algorithm for I is equal to 0. It's a very simple algorithm. I don't have to explain what it is doing, and I am writing in a manner which is called the pseudocode. It's like Pascal or C, but not exactly like following all the syntax and everything. But it should be clear to you what I am trying to do. Can you see? Can you see what I am writing? Okay. So Cij is equal to Aij plus Bij. Okay, and that is end for another end for n. Okay, so this is the algorithm for adding two matrices and creating a new matrix C. Okay, so let's see how much time does it take. Okay, now as you know, it all depends on which computer you run this program, and also I have not told you how this for loop is executed within the computer. Okay, so there are many nitty-gritty details which are missing, without which you cannot tell exactly what is the time for this program to run, right? But we are not interested on exact timing, because that's not possible. I don't know on which machine it will run at all, after all. So my motivation is to compare algorithms, the comparison should be independent on the machine. It should be independent of the machine. It should be independent of how each operation is being executed. Okay. So how to do that? For this one, what we will do, we will count basic steps of the algorithm. How many steps are there? Okay, which is independent of the machine. Okay. Here, if you see, this for is a basic step, right? So for is executed. For example, it will be checked whether I is equal to 0, whether I is less than n. Sorry, it will be first I will be 0, then it will be checked whether I is less than n, then I will be increased by 1. Okay, so that's this step we will do. Okay, then the next for we will do that similarly. Then Cij is equal to Aij plus Bij. This is just an assignment. Okay, but suppose this is a one count. Basically, this is a constant time. It may be say 4 millisecond or 400 millisecond, but whatever it is constant. It's a one step, one count. Second is another one count. This is also one count, right? So now let's see how many times this one is getting executed. How many times this is executed? N times it is getting executed, roughly. Okay. How many times this is executed? So this gives me total count of n. How many times this is getting executed? Is it executed n times? It's not n, because this is within this for loop. So which is executed n times, and this is it itself is getting executed n times. So n times n is roughly n squared time, right? So this is roughly n squared times, and this one is getting executed another n squared. Okay, so if we see, so total steps, roughly I get n plus 2n square, right? Roughly. If n is the input size, this is the total time, total number of steps. Now again, we have already ignored some of the things, but is it very important to know that this is 2n square? It's not. It's not, because already I have taken the liberty of not putting the exact constant before n square here. It will not take exactly n square step, because each step you don't know how much time does it take. So this constant is not very important. What is important to us that it is n square, not n. It is n square, not n. Whether it is n cube, n square, this is what which is important. Okay, and this is also independent of machine, independent of particular constants. Okay, so this is the motivation of introducing the asymptotic notations. Okay, why this BGO notation was introduced? To compare the algorithm where the constants are unimportant. Okay, so did you get the notion why did you this order notation was invented? Okay, now let me first go over the definition of BGO. Okay, what is the definition of BGO? We say, so now we are going to the formal definition of BGO. So this is BGO notation. Okay, we say a function fn is of the order of another function gn if and only if. Does people know what is if and only if? Okay, if and this is both necessary and sufficient. Okay, most of the time I will be writing if and only if as IFF. This is a usual notation. Okay, so if and only if there exist positive constants C and n0 such that fn is less than equal to C times gn for all n greater than equal to n0. Do you know this definition? Probably you know this definition already, but let me just tell you why this definition. What is the motivation for this definition? If you have seen here the previous slide, this n plus 2n square, when n is very large, which factor will dominate the value? N square will take over n. If you plot the graph, it will be mostly parabolic. When n is very large, n does not come into picture that much. Okay, so we are interested to know how the algorithm will behave, the time complexity of the algorithm will behave when input is very large. Okay, so that's our goal behind defining this order notation. So we should define something which will capture this notion. When n is very large, what is the time complexity of the algorithm? Okay. Okay, and this is precisely being done in this definition. If you see it very carefully, we are saying fn is order of gn. Okay, and there are two constants which are very important, C and n naught. And how is it captured? When n is very large, it is captured by this n is greater than n naught. You fix n naught. N naught is a constant. N naught is a constant. Okay, you fix once. But when n is greater than that, that means basically n is very large, then fn must be less than equal to this function gn within a constant factor. Okay, so as if gn is a function which is capping this function fn when n is very large from above. So if you plot the graph, it should be something like this. So suppose if you have fn, so n and fn, initially probably like this, then fn is this. So what this gn saying, Okay, Gn initially I don't know, but when n is large, Gn is something like this. So this is Fn, this is Gn. So maybe I can put maybe n naught here. When n is greater than n naught, Gn is above Fn. So suppose this is C times Gn. Okay, I am plotting. So this Gn is always above Fn when n is greater than n naught. So then you can say that Fn is of the order of Gn. So let's take an example that will make it clear. So let's see. Suppose I have a function Fn is equal to say 5n plus 1. Okay, this is my Fn. Okay. Now let me take Gn is equal to say n. Can I say, so question is, can I say Fn is equal to order of Gn? Can I say this? Go back to the definition. What do I have to do? I have to find out two constants, n naught and c, and then we have to prove that Fn is less than equal to c times Gn when n is greater than n naught. Can't we do this here? We can easily do it. How? I can always say Fn is always less than equal to say 6n for n greater than 100. Can't I say this? We can say this, right? So now I have already shown you a constant c, this is c in my definition, a constant 100, this is n naught. So I have given you c, I have given you n naught. So Gn must be this function n. Is it clear to you? Why Fn is equal to order of n now? Any question? Okay. So let us take some more example. So let's take Fn is equal to say 10n square 5n plus 6. Can you tell me what is the order of this? This is order of n square. Can you prove it? How can you prove it? What do you have to do to prove that it is order of n square? We have to find out. No, Gn has been given. Gn is what? Gn is n square. So we have to find out two constants, c and n naught. Okay. So tell me what should be the c and n naught. So show me Fn is less than equal to some c times n square for n greater than equal to some constant n naught. So find out n naught, find out c. So what should be the answer? What is c? 11. Probably 11 is fine. Or the safest one is replace each one of this 10n square, take it as 10n square. But 5n you replace it as 5n square, because 5n is always less than equal to 5n square for n say greater than equal to 100. Okay. 6 also replace with 6n square. I am being very pessimistic, but it's fine. I have to find out a constant, not the base constant here. Okay, probably this is not the best constant, but I have to find out a constant. Okay, so I can always say Fn is less than equal to 10n square plus 5n square plus 6n square for n greater than equal to, even 1 is fine, right? Greater than equal to 1 is also fine. Okay, so that means this is less than equal to 1521 n square for n greater than 1. So this is my n naught, 21 is my c. So Fn is of the order of n square. Everybody understood? Yes.
Sir, here we have chosen Gn as n square, sir.
Right.
But we have to choose such a G such that.
I'm coming to this point. I'm coming to your point. That's a very good question, actually. I'm coming to your point. So what his question is, see, instead of choosing, so let's see, in this example, instead of choosing, I could have choosing n square, I could have chosen n cube, right? and this is still valid. By definition, this function fn is also of the order of n cube, because you can always say fn is less than equal to 21 n cube for n greater than equal to 1. So by definition, fn is also of the order of n cube. But go back to your ultimate motivation. Why did we invent all this? To know the complexity of the time complexity of the or space complexity of the algorithms. So what should be your goal? To know the best possible asymptotic complexity, the best possible time complexity. Your analysis should be the best possible as much as you can. So definitely n square is better than n cube in this respect here. So if somebody says that this same algorithm is of the order of n square and somebody else says that it is of the order of n cube, which one would you prefer? N square, because that's a better analysis. Okay, and there lies the whole point. Definitely, given a function, you can say this is, and I ask you what is the order of it, definitely you can say it is of the order of 2 to the power 2 to the power 2 to the power some power of 2 then n. You give a very large function, which is true, which is correct. The statement is correct, but it is wrong in the sense that this is not a correct picture at all. Okay, so this is very important. What he has pointed out, that you give the analysis as best as possible, whatever you can do. Okay, so keep it lower, because this is an upper bound. Remember, this order is an upper bound to your function fn, to your complexity. So you should try to keep it down. You should try to match the graph from above as much as possible. So you should keep it down. Upper bound should be as low as possible. Okay, so I hope this you remember throughout this course. This is very important, that you should analyze something in your best possible way. Okay, well, this is your question, right? Okay, now let me take another example. Say fn is equal to, say, 6 2 to the power n plus n square. Can you tell me what should be the order? Order of what? 2 to the power n. Because definitely I'm not going to write everything here. You can definitely say that fn is less than equal to, say, 7 2 to the power n for n greater than. You don't need to prove this, right? This is obvious. Okay, so you have found 7, you have found 1, is order of 2n. Okay, now as he has asked the question already, so what is the next question? The next question should be asked, that is this order 2 to the power n is the best thing? Can we make it lower? Because I already told you our ultimate goal should be to make it lower. But can we do it? Can we make it lower? This less than 2 to the power n? No, we cannot, because you cannot avoid 2 to the power n here. You cannot avoid 2 to the power n here. Okay, you cannot say this is order of n square.
The previous problem, we are given, if n is greater than 2, then 2 to the power n is always less than n square. Then you have written, then
Which one? This one?
So 6 into 2 to the power n plus n square.
Right.
Sir, for n greater than 2.
Okay, so yeah, or we make it n greater than 10.
So then also, for any value of n greater than 2, 2 to the power n is always less than n square.
2 to the power n is always less than n square. 2 to the power n is not less than n square. What is 2 to the power 5? 32. What is n square? 25. And that's it. If you plot the graph of 2 to the power n and n square, you will see 2 to the power n will grow like anything. Let me give you the idea. When n is equal to, say, 30, what is n square? 900. So let's take 2 to the power n millimeter and n square millimeter. Okay, n square millimeter is 900 millimeter, which you can grasp. But 2 to the power 30 millimeter is something like the distance from here to moon. just calculate. I don't know whether you already know it. If you take a paper, newspaper or some paper, and you fold it 30 times, the thickness of it would be such that it will be the distance from here to moon. That should give you the idea how this function grows, how fast. So if some algorithm has a complexity of some 2 to the power n, most probably for a very moderate input, when n is equal to 30, it will not give the output even in your lifetime. Probably not even in the lifetime of the whole human being. It's so large. And that's the whole point here. Why should we bother with designing algorithms? You can probably solve a problem in many different ways. You can do it in a naive way, and that naive way probably will give you some algorithm which is very bad, which will have a complexity of 2 to the power n. But somebody smart will come and give you an algorithm which has a complexity, say, n square. So he will solve the problem, say, within a 1 day, or even with some fast machine within a minute. And your algorithm, which is a naive one, which did not take much time to design, will never give you the output in your lifetime. So that's the whole point of designing algorithm. And that's the whole point of analysis also. After designing, you show that this is really good. Okay? Yes.
Now, in all these examples, what we've been doing is we've been looking at a function,
Right.
and then we have been deducing the gn.
Right.
Cannot it be that gn is totally something different? And like, if it is something like that, how do you work it out?
No. See, if the function is given, it's up to you what gn you choose. But I told you the thing is you should choose the one which is best possible. Okay. But in our cases, what will happen? The algorithm will be given. We have to choose. Actually, Fn will not be given. We have to design everything. We have to find out our own gn. Nobody will give us the gn. If gn is given, then the problem is solved. Basically, we have the precise problem is to find the right gn.
Sir, what will be the basis for the choice of GN? Just for which factor will be dominating?
That is the whole point of this course. To know how to design algorithm, how to choose GN, what is GN and all these things. I mean, there is no hard and fast rule. I cannot give you a formula to choose GN. You have to think over and you have to come up with the right answer. Okay? So this is a course where it's something like sometimes it will be a puzzle. You have to really solve the puzzle. There is no hard and fast rule. Okay, now here comes the question. So already we have seen what is the upper bound order of a function. But as I told you, after you have taken an upper bound, you need to know whether this is the best. Okay. So similarly, let's go back to the algorithm. Suppose you have already analyzed the algorithm and you have shown that this is the upper bound of this algorithm. This is the order of the algorithm. So next question one should ask, have you analyzed this the best possible way? Can I come and say, okay, this analysis was not good, I can analyze it better? So your question is, no, then I would require to prove that my analysis is the best. You cannot do anything better. Right? Naturally, that should be the next question, means how to do this. So to capture this notion now, what one do is to define the lower bound. What is the lower bound? You will say that this algorithm will take at least this time. So upper bound was at most this time. It was less than equal to. So suppose if you can say that this algorithm will take, no matter what it is, it will take in the worst case at least this time. In the worst case, mind that we are trying to analyze in the worst case scenario. And nothing can be worse than this. What is the time for that? Okay. For some input, probably algorithm will work better, but that's not our botheration here. We are trying to see what is the worst case behavior for some input. Okay. So if you can say that this algorithm will take at least this much of time in the worst case, and I have shown you that this is also at most, then my analysis is the best. Nobody can come and say that I could have analyzed it better. Okay, so there comes the question of lower bound, which is big omega notation. Have you seen this notation? Big omega. Okay, so big omega is again Fn is omega Gn if and only if there exist constants C and N naught such that it's the same thing, only is Fn is this time greater than equal to C times Gn for n greater than equal to. So this is the change. Previously it was less than equal to, now it is greater than equal to. Okay, then you say Fn is of the not order of omega Gn. Fn is omega Gn. Okay, so with this, so you write the definition and just see what does it mean. In terms of graph, it means you are trying to find out a Gn which will run below this Fn this time instead of going above. Okay, so have you written this already? Okay, so let me go back to this some previous example. Say this one. So I take the same function. Say Fn is equal to 10n square 5n plus 6. Can I claim that this is omega what? What would you say now, n or n square? Which will you prefer? This is now just the opposite. You will try to do not lowest, the highest one, because now you are trying to do a lower bound. So you should feed your graph from below. So it should be as high as possible. The previous case, it was trying to feed the graph Fn from above. So you are trying to find out as low as possible. So instead of saying omega n, if somebody says this is omega n square, that's a better answer. Definitely this is omega n. You can always say that this Fn is greater than equal to say n for n greater than equal to 100. Definitely that is true. But I can also say this is greater than equal to n square for n greater than 100. That is also true. And which is a better analysis than n now. So this is omega of n square. Because why? Because Fn is greater than equal to n square for say n greater than 100. So I have given you n naught, I have given you constant 1 here. So this should be omega n square. It's just the opposite concept of order. One is upper bound, this is lower bound. Okay, so this is the omega concept. Okay, now we know what is order, we know what is omega. Now comes the notation called the theta notation. Okay, what is theta notation? So let's take this Fn all again. It was 10n square plus 5n plus 6. I already proved Fn is of the order of n square. I also showed this is omega of n square. Right? If these two, so both these cases Gn are same. It is of the order of Gn, it is also omega of Gn. Okay, so in that case you say Fn is theta of n square. So what is the definition? Basically Fn is theta Gn if and only if Fn is order of Gn and Fn is omega of Gn. If both are true, the same function Gn, then it is theta of Gn. Okay, so now you can see what should be the ultimate goal. of analyzing an algorithm. Ultimate goal is to prove something is theta. Then nobody can question you, at least with this analysis of this algorithm. Because you have already shown this is at least, this should get at least, and you have also shown I have proved that this is also at most. So you have achieved the optimal. So this is all optimal algorithm or optimal analysis in this case. If you can show something is theta, then that analysis is optimal.
What is the significance of
That's what I was explaining all the time. Significance of this theta is that you have shown that this analysis is the best. You have shown that this analysis was the best because you have proved that nobody can improve this analysis anymore. So only if you prove only order, somebody may ask you a question: why it is order of n square? Why not order of n? Now, if you show this is omega of n square, this question is gone. Nobody can ask you. It cannot be reduced to order of n. If you have proved something is omega of n square, you cannot prove that it is order of n then. Okay. Similarly, if you only prove it is omega of n square, somebody will come and ask why not it is omega of n cube then. But then you have already shown, suppose it is order of n square also, nobody can ask you that question. It's a tight analysis, and that's the significance of theta. Any more question on this? This is very important. Before we go into the design analysis of algorithm, this notion you should learn by heart. Because if you have confusion here, the entire course you will have trouble. This is very basic, the analysis part. Okay, and analysis is a very basic thing for designing algorithm. Because you would know how good is my algorithm only if you analyze it with respect to time complexity, space complexity. And these are the tools to do this, by which you can see how good is your algorithm. Okay.
So there is no such thing as the best possible constants. The constants can remain
Yeah.
constant.
Because you don't have any handle on constant. Constants will depend on which machine you are running the program, right? Because each step actually is a lots of steps within the computer. Like even addition of two numbers. In terms of assembly language, what it will take? It will bring from the memory one number. It will bring another number probably from the memory. It will add, keep it in a register. It will move the register to the memory again. You didn't take care of all this. And how each step is taking inside the computer, how many milliseconds, how many microseconds, you didn't take care of it. So what is the point of putting a constant at all there? Okay, and that's the whole point of developing this tool, that we don't bother about the constants. We bother how the algorithm behaves asymptotically. What does it mean asymptotically? When input is very large. In the worst case, how does it behave? Okay. Now, now there are two basic things. Given an algorithm, you can analyze in a best possible way and say that this analysis is optimal, right? Because you have proved that this is theta of some gn, the analysis. But you have written the algorithm to solve some problem. So let's take the problem as sorting. Okay, so let's take the problem of sorting. Now sorting can be solved, as you have already seen, with different algorithms, maybe quick sort, maybe heap sort, merge sort, insertion sort, bubble sort, so many algorithms. Okay, but the problem is same, is sorting of numbers, right? So there is a concept of problem which is I call a P, and that algorithm A. Okay, now given a particular algorithm, suppose quick sort, you already know its worst case time complexity is of the order of n square. Okay, and it cannot be made better, because there are certain cases where it will run in that much time. So actually the quick sort algorithm as it is given has a complexity theta of n square. That particular algorithm has theta of n square. Okay, but that does not mean the problem sorting has a lower bound of omega n square or upper, sorry, it has a lower bound of omega n square, because somebody may give another algorithm which may solve it better. Like I give you heap sort. Heap sort is an algorithm which will solve the sorting problem in less time, in log n time. So the problem sorting is not theta of n square. If you give an algorithm A to solve the problem and say that algorithm A runs in order of Gn, what does it? It implies that the problem can be solved in order of Gn, because you have given one method to solve it in order of Gn. But it does not mean that the problem has to have a complexity of omega G, because somebody else may give you another better algorithm until unless you prove it. Okay, so what I am trying to point out, there is a distinction between the best possible way of analyzing one particular algorithm, and there is another notion, what is the best possible way to solve a problem P. What is the best possible way to analyze algorithm A? What is the best possible way to solve P? These are two different notions. Okay, so when we say that the algorithm A has complexity theta n square, algorithm A, that means you have analyzed the algorithm A in the best possible way. But that does not mean you have solved the problem P in the best possible way. For that, you need to prove that the problem P has to take, no matter what algorithm you choose, has to take say omega of n square or omega of some function G. So no matter what algorithm you take, it will always spend at least this much of time. That's a harder problem actually. Okay, if you show that and also give an algorithm which solves the problem in the same time, then you have solved the problem in optimal time. Is this clear? This people get confused with these notations. What I am saying, people have real confusion over these concepts. Is it clear what I am saying? Optimal algorithm for a problem P, optimal analysis for an algorithm A. So can you make the distinction now? Okay, yes. So what I am saying, suppose I have an algorithm A to solve P. So P is this is the algorithm. This is the problem. So this analysis is optimal does not mean P is solved optimally. Can you get this point? This analysis, what analysis you have done, that is optimal, but that does not mean you have solved the problem P optimally, because somebody else give you another algorithm which is better than this. Okay, and this problem is problem solved optimally requires to show that no algorithm is better. Okay, so make this distinction. Like sorting again. So heap sort is the algorithm which solves it in what? Heap sort takes how much time? N log n, and it can be proved that sorting cannot be solved in less than n log n time, if there is a condition that if only comparisons are used. So heap sort solves the problem of sorting in optimal time, but quicksort does not solve the sorting in optimal time, because quicksort takes order n square time, which is more than n log n. Quick sort does not solve the sorting in optimal time. Heap sort solves the problem of optimal time. But quick sort has the analysis optimal analysis n square. You cannot analyze quick sort better. And that's the distinction I am trying to make. All right? Yes.
Given any problem, can we decide that this is the optimal way of solving it? Like for sorting.
Yeah, right. So then you have to prove this. This is not the question of decision. This is a question of proving. So if you have to show that sorting cannot be solved more in less than n log n time, you have to show this. You have to prove it. That's not a very easy task. So you have to develop some tools or some way to show that no matter how you design an algorithm, it will not solve it in better time. Okay, then only you can decide. It is not automatic. This requires proof. This requires thinking a lot. Okay, have I answered your question? I don't know who asked. Okay, now let me go over some. Yes, let me go over some of the well-known complexities which we will encounter all the time. Okay, so we'll see like order of n. This is called linear time. Sometimes we will see algorithm order of n square or theta of n square. This is quadratic time. Quadratic time. Order of n cube. Sometimes we will see this cubic. Order of 2 to the power n or something to the power n. This is called exponential algorithm or exponential time algorithm. Okay, and sometimes we will see order of log 2n, okay, which is the logarithmic time. Sometimes we will see order of n log n. Sometimes we will see order of 1, constant time. Okay, these are very usual ones which we will encounter in this course. Sometimes it will be in log square n also. Okay, but let me just point out one thing. Suppose I have a complexity which is order of say log 2n. Can I say this is also order of log say 100n? So you know this. This base does not matter because I can always express log 2n as some constant time of log 100n and vice versa actually with the usual formula. Okay, so since this base does not matter, most of the time we'll say that order of log n. We'll not mention what is the base. It's understood. You take your constant. Most of the time it will be 2, but we will not mention because it does not matter in our notation. So we'll say just order of log n. All right. Now just tell me, suppose I have order of n log n and another algorithm order of n plus n square. Which one is better? So this is better, right? Okay, suppose I have a function fn n 2 to the power n and another one say f prime n 6n square 1 by 100. Which one is better?
Same. Same.
Both are same. Both are order 2 to the power 2n. Okay. Now think over this. Which one is better? Log 3n 100n. Another f prime n is. Oh, you cannot see it.
Both are same, yes, sir.
Fn and f prime n?
Same.
Very good. Both are same. Because 2 to the power log 2n is n. So don't get deceived by all this. Okay? Sometimes people, you will see something like this. So you should be careful. So both are same.
Sir, can there be anything as such order of n plus n square? What you have just
No. Yeah, I can write this, but actually this means order of n square. Basically, I have taken Gn as n plus n square, but I should not have taken probably. It's order of n square.
So if it is something on the order of log of n square, that becomes.
That's a very good point. So he's saying, suppose I have log of n square. Can you say this is order of log n?
Yes, sir.
So log of n to the power some constant is always order of log n. Because by the theory of logs, all this constant will come, power constant in the power will come in front as constant. Okay, so that's it for the asymptotic analysis. We will have a break and we'll come back to the next one.